So remember from the last lecture, we had z was a complex number, and it could be written as a plus bi in Cartesian coordinates, or r cosine theta plus I r sine theta in polar coordinates. Now, we're going to derive Euler's formula, and we're actually going to use a differential equations method to do that. So we're going to set r equal to 1. And then this will just make it a little bit easier. So z equals cosine theta. We could keep r in. It would just always be a constant factor out in the front. Plus I sine theta. Okay, and we'd like to find out more about this number, cosine theta plus I sine theta. So let's actually take a derivative with respect to theta. What happens there? Derivative of cosine theta is negative sine theta. Derivative of I sine theta, the I stays out as a constant, and we get cosine theta. And then we're also going to factor out an I. The reason for doing it is to make it look more like this. Because then if we take out an I from here, we're left with cosine theta. This is a negative 1, which is I squared. So if we take out an I from here, we get plus I. Check that out, make sure you believe that, times sine theta. But then this part looks exactly like this up here. So actually the derivative is iz. Okay, and now this is a differential equation that we know how to solve by separation of variables. I is just a constant, so we're just going to treat it like that. So dz, divide both sides by z, multiply both sides by d theta here. And then, okay, there's a little bit of a hand-wavy thing here. If we take the integral, if we have a real variable x and take the integral of dx over x, that is natural log of absolute value of x plus c. And we've talked a lot about this absolute value. If it's complex, it's sort of natural log of z. We're not going to take absolute value. It's not distance from 0. It's not r. There's more going on here. You can't do this on the whole complex plane. You can do it on the complex plane with a slit. This is complex analysis, more than we need to get in here, but note there's more to think about here. But roughly, it's natural log of z. Okay, and then the integral of this side is I theta plus a constant. Okay, and if we just don't worry about weird things in the complex plane there, then we get z is e to the I theta plus c, which is e to the c times e to the I theta, and this is some constant k times e to the I theta. C, because we were in complex numbers, c can be a complex number, so k can be any complex number, so we don't have to worry about saying k is greater than 0. Okay, and then let's just go back to the top to get an initial value. Let's sub the easiest value, which is theta equals 0. Then, because we know what the original function is also. Z is cosine of 0 is 1, plus I sine of 0 is 0, so z is 1. This is a weird thing. We're solving a differential equation, but we knew what the answer was. Okay, so we're going to sub theta comma z is 0, 1 in here. And then we get 1 equals, on the right-hand side, we get k times e to the 0, which is 1. So k equals 1, so that means z is e to the I theta. So that's fun, because we knew what the answer was, and we got a different looking answer. That means those must be the same. So here we get, then, Euler's formula, which is e to the I theta equals cosine theta plus I sine theta. Very famous formula. You'll notice Euler's name has already come up twice in this course. Euler did a ton of math, so maybe naming something after Euler isn't that wise. People might not know what that is. There are other things also called Euler's formula, unfortunately. But one beautiful thing that I can't let go of now that this has come up is also Euler's identity. There are other things called Euler's identity as well, unfortunately. But if we set theta equal to pi in this formula, then we get e to the I pi equals cosine of pi is negative 1 plus I sine of pi is 0. So we get this equation, and then adding 1 to both sides, we get this beautiful equation. I think this is the most beautiful equation in math. E to the I pi plus 1 equals 0. Why is it beautiful? It's got 1, which is the identity of multiplication, so important number. 0 is the identity of addition. 0 and 1 are the two most important numbers. And then we've got these two most important irrational numbers, e and pi, which come up everywhere. And then we've got I, which is the most fundamental number in complex number theory. And they're all related by one equation, so that's really cool. And actually, my favorite math teacher from high school had a license plate that read this, EIPI 1, 0. That was his license plate, which of course references this identity.